Thank you, Ron, for the introduction, and I'd like to thank the organizers for inviting me to give this talk and to and for allowing this to happen over Zoom. I'm going to talk about a joint work with Alan Lew from Carnegie Mellon and Eran Nevo and Orit Raz, or my colleagues here at the Hebrew University. They talked about our work on the rigidity of random graphs, and I'm going to start by giving a very brief introduction on combinatorial rigidity, which is a beautiful and deep theory, and I'm going to try to just give a brief overview on the most important concepts that are needed for this talk. And of course, please feel free to stop me if you have any questions. Okay, so the main object that combinatorial rigidity deals with is a framework, which is a pair consisting of a graph denoted here by G, and a map free from the vertices to a d-dimensional Euclidean space, RD. And I think the best way to imagine it is to think of the vertices as points in RD, and the edges as some rigid bars that somehow determine the distances between these vertices. And such a and of course we'll see examples very shortly. And so such a framework is called globally rigid if basically the map phi is determined up to isometry of RD by the set of the distances between adjacent vertices. And the second, perhaps more important notion is that a framework is called a rigid or locally rigid if there's no motion. You cannot move the vertices from the map phi in a continuous way, in a way that preserves all the distances between adjacent vertices. Of course, except what I call here a trivial motions, which come from a motion of the entire space. So let's see a couple of examples when these equal to 2. So I can draw it here on the iPad. So the first example is, let's say, a clique or a triangle. So this graph is indeed rigid. And I'm sorry, and of course, I can move the vertices in a way that preserve all the pairwise distances. I can do it by translation, like I do here, or rotation, like I try to do here. And these are the trivial motions, and in this case of a triangle, these are the only set of motions that are available. So this graph is indeed rigid. If I would add another vertex, like here, are connected to this one, then this graph will not be rigid because I can just move this new vertex in a way that preserves all the distances between the edges of the graph, but for instance, it will not preserve the distance between the new guy and this guy. So this graph, this motion does not arise from an isometry of the plane. Hence, this graph is not rigid. If I want to make it rigid, I can add another edge. So this is an example of a rigid graph. So this is rigid in the dimension 2. But I want to claim that it's not globally rigid, and the reason is that I can take, for instance, this vertex right here. It has degree 2, so its neighbors form and they span an affine hyperplane, or in other words, a line, and then I can. Oops, I wanted to be in a different color. I'm sorry. And then I can look at this line and reflect the location of this vertex with respect to this line. And if this was 5x, I can replace it by some phi prime of x, and of course, phi and phi prime have the same distance profile. So I think this I hope these examples were helpful, and let's just draw two simple observations from the discussion here. One is that if a graph is rigid, or if a framework is rigid, then its graph has a minimum degree at least d. This was the first example that we saw. I could just move one vertex, and if a graph is global rigid, then its minimum degree is at least d+1. Otherwise, I can reflect its location with respect to the affine hyperplane spanned by its neighbors. Okay. So the basic question about combinatorial rigidity is, given a framework, is it rigid? And this question has a very nice history, both in mathematics and in physics. So in mathematics, the very famous Cauchy's rigidity theorem talks about the rigidity in R3 of convex polytopes, and actually its proof appears in the proofs from the book. It is a very nice proof. Physicists also, of course, dealt with this concept, and this goes back to Maxwell. And naturally, it's a concept that has a lot of applications in engineering, in robotics, and so on. Mathematically, it turns out that deciding if a given framework is rigid is a hard problem, both mathematically and computationally. So, versus it even can be hard in when these equal to 2. But perhaps surprisingly, the question if a framework is rigid or not depends quite a lot on the map phi. And it turns out that if phis are generic, that is so I guess that in this way, I guess that it's random by some continuous distribution, or formally you want to say that the entries of phi are algebraically independent over the rationals or over the integers. In that case, rigidity is a somewhat simpler property, and in particular, it depends only on the graph G. Like all generic maps are the same, and moreover, it's a linear algebraic property. Sorry, and this was discovered by Asimov and Roth in the late 70s, and maybe just try to explain very briefly what was their discovery. So suppose that you take this map phi. So I remind you that phi is a map from the vertices to RD, and map it by some function which we'll call let's say f sub g, because this function depends on the graph, to the set of distances px minus phi y over all the edges xy in E. So this should be here in E. This is a map from R to the dv, right? Because every vertex has the d coordinate. So a vector in RDV describes phi to R to the E. And if you think about it, rigidity basically deals with inverting this function. So you have some point phi in R to the dv, and it is mapped to some other point. So rigidity asks you whether you can find some path starting at phi, which is non-trivial in the sense that it doesn't come from an isometry like this, where such that all the points here are mapped to the same place, right? You want to preserve all the pairwise, all the distances between the edges, between adjacent vertices, in a non-trivial way. And what Asimov and Roth did. They said, well, if this fee that I do here, so this fee is generic, then you can reduce this to a seemingly simpler problem, which is you don't have to describe the entire continuous motion, only the direction in which you begin. So just find some direction. Let's call it Q, such that, and I'll write it here on the right, such that if you take fg of phi plus t for time times q, the derivative or the differential of this function at times t equals 0 is 0. So just infinitesimally find a direction in which you you don't change the distances. So this, of course, reduces to some question in linear algebra, which comes from differentiating this function fg at the point phi, and if you do the math, you discover this matrix. It's a dv by e matrix. We call it R, the rigidity matrix, and at the column that corresponds to the edge xy, so xy is an edge, has two non-zero blocks of coordinates at the d coordinates of x. It has the vector phi x minus phi y, and in the coordinates of y, it has phi y minus phi x. And this is just what you get when you derive this function f sub g that I mentioned. And then a graph is okay. And now, as I mentioned, rigidity is now not a framework property, but a graph property. And the graph is called the rigid if the rank of this matrix is maximal, and maximal being d times v minus d plus 1 choose 2, and this needs to happen for a generic phi, or for all generic phi, or for some phi. It's all the same, and just to reiterate the idea, the left kernel of this matrix is in a correspondence with motions of the vertices that infinitesimally preserve the distance of adjacent vertices, and this explains partly this d plus 1 choose 2 number. These are the these come from the dimension of the isometries. So you have d translations plus d choose 2 rotations, and these are the trivial motions. Okay, so this is the notion that we have studied. And let's before we delve into random things, let's see what this notion, or what do we know about this notion in low dimensions. So for d equal to 1, rigidity on the line is exactly graph connectivity. So intuitively, that is not hard to say that if you have a connected graph, there is only one way to move all the vertices. But another way to say it is to observe that if rigidity matrix R in if this equal to 1 is exactly what is called the up to some scaling, the boundary matrix of the graph for monos as the oriented incidence matrix of the graph, which, as we know, captures its connectivity. So this is the simplest case. In a sense, it's nice to have a concept that extends such a beautiful and fundamental property like connectivity. When this is equal to 2, planar rigidity, that is a very well studied and well understood notion. And so going back to Olaman in the 70s and others. So when I say well understood, I mean that wrote with some very explicit combinatorial characterizations of two rigid graphs and algorithmic and efficient algorithms to determine or decide whether a graph is rigid in the plane. And the names that I wrote here are a bunch of different results giving different characterizations of two-dimensional rigidity. For d greater than 2, the situation is much less understood, and in fact, I think perhaps the major open problem in combinatorial rigidity is to find a nice or less nice, that's up to you, combinatorial characterization of three rigid graphs, and there are some really seemingly simple conjectures about three-dimensional rigidity that we have no idea how to attack. And I guess in my opinion, whenever you have such an important and not so well understood combinatorial concept, it makes sense to test it in some average case graphs, and the problem that we dealt with here is to understand for which values of p a GNP graph is rigid. And this is the topic of this work.
Yuval, I have a question.
Yes, please.
So there is the concept of de-rigidity, and there were the previous concepts of rigid and globally rigid. So what is the connection between de-rigidity and rigid and globally rigid?
Okay, so in general, a global rigidity in dimension D implies, of course, a rigidity, and the other direction is false. And there are some theorems we will see, or one that connects between like that shows in what sense can you strengthen rigidity of a graph to obtain global rigidity? But I would say that in general, both mathematically and computationally, a global rigidity is a harder property to understand. So, for example, I mentioned that two rigidity is co-NP hard. Well, it turns out that a global one-dimensional rigidity is already NP hard or co-NP hard. So it's a harder concept.
Right. Okay. Well, thanks a lot. Very good.
Okay. Good. Thank you. And then, please, if you have any more questions, I'm happy to answer. Okay. Okay. So let's. I'd like to give a brief overview of previous results. So when this equal to 1, I mentioned that rigidity is connectivity. This is a classical topic in the study of random graphs. So we know from Erdos-Rényi what is the critical probability for GNP connectivity, and we know that, and we in fact even know a stronger, what we call a heating time result, which means that if we do a random graph process where in each step we add a new random edge chosen uniformly, the moment that the graph becomes connected is equal with high probability to the moment in which its minimum degree is 1, or that it doesn't have any isolated vertices. So this is a classical result for d equal to 2. Sorry. So now we are in the two-dimensional case. So based on the characterization that I briefly mentioned of Lovaas and Gemini, Jackson, Servatus, and Servatus found the exact behavior of the critical probability, the sharp threshold probability of two-dimensional rigidity, and it coincides with the having minimum degree 2, and it was based on the fact that we understand two rigidity very well. Prior to this work, there were a couple of works on 3 and above dimensional rigidity, and they were able to obtain the correct order of the critical probability. And our result, and this is the main result of this work, is that we're able to extend the heating time result of graph connectivity to d-dimensional rigidity for every D. So I forgot to write here that fix some D at least one. Sorry. And we were able to show that in the random graph process that I mentioned, the graph becomes rigid in the very moment its minimum degree becomes D. Of course, with high probability, and this, by previous works that I mentioned, also implied that the graph becomes globally rigid at the very moment its minimum degree becomes D+1. So once these trivial degree obstacles are put away, then we have rigidity. So here are a bunch of remarks about this theorem. So what is that, as you mentioned, one side is deterministically and easily true. You got to have the minimum degree to have rigidity. And in fact, a series of works, so this is not an easy theorem, based on a series of papers on global rigidity. One of the things we know is that D+1 rigid graphs are globally rigid. So therefore, the first point in our theorem immediately implies the second point. Another remark, so 3 more remarks. First of all, is that I mean, we understand very well the degree sequence of a random graph. So of course, this stopping time result implies what is the critical probability for these properties. This is well known. And the last point, I'll just mention it, is that I mentioned that rigidity is a very rich topic, and one attempt in this theory was to find some axioms that would capture rigidity, and this actually failed in the sense that it led to various theories, all like which are variants of rigidity, which are called abstract rigidity matrix, and it turns out that our proofs are relied on basically only and all of these abstract axioms. So it actually applies in a more broader context. So the next thing I want to do is to tell about I think 1.5 nice ideas from the proof, and then mention some open questions. So unless there are any questions, I will go on. Okay. So my goal now is to prove that at the moment that the random graph process acquires a minimum degree of D, it becomes rigid. And the following concept that actually comes from matroid theory will be helpful. So this is called the closure of a graph, and we call it CD of G. And so given a graph G, we defined another graph, a larger graph on the same vertex set, which contains all the pairs x, y, such that if I would, such that the a column of the edge x, y in this rigidity matrix is in the span, in the column space of the rigidity matrix of G. Or in other words, these are all the edges for which if I will add them to G, I will not increase the rank of the rigidity matrix. So, and it makes sense, I guess, that if you want to prove that a graph is rigid as an intermediate step, try to show that its closure is large. And this is what we want to do. And for this method, there's very nice and cute argument that gives that. So first, let's mention this observation, which is that in the a random graph process, or in fact in any way that you would add edges one by one, the event that the mth edge that you add, so this em here, is not in the closure of your current graph. This can only occur, or it will occur exactly, but in any point at most, dn minus d plus 1 choose 2 times. And the reason is, of course, very simple. Every time this happens, the rank increases by 1, and the maximal rank is this d minus d plus 1 choose 2. So this cannot occur more than this number of times. And then on the other hand, this in the random graph process, these edges are selected uniformly at random. So intuitively, at least, if M is sufficiently large, and if you would assume that the closure after M steps is relatively small, this is this feels probabilistically expensive, because this means that you would have to choose an edge from the supposedly small closure too many times. Let me say it a bit more concretely. Suppose that in every step you would use an independent uniform 0, 1 random variable to decide decide whether this event occurs, namely to choose whether whether you sample from the closure or from its complement. This would induce a coupling between the size of the closure after M steps and these independent random variables, which would actually mean that this event here, that the closure is small, is contained in the event that the number of eyes between 1 and M, such that this independent random variable, let's call it Ri, is greater than alpha. So this number must be smaller than dn minus d plus 1 just 2 deterministically, because every time this occurs, you you pick an edge that is not in the closure, hence you increase the rank by 1. And this is, of course, I mean, it's an observation which is not unique to rigidity. It applies every time you have a process in which you add columns from some matrix in a random way. So this is the one idea, and then once you've have that, since we were aiming for M, which is relatively large, the M that we want to aim for is the stopping time of having minimum degree, which is roughly of the order of n log n. So if you use the inequality I mentioned here, you can obtain the first point that asymptotically almost surely this the closure is have density which is close to a 1. Then in addition, there are two other facts that that this closure has, which is a 1 if the closure contains a k d plus 2 minus an edge. So let's say in d equal to, it would contain this graph. Then it must also contain this edge as well, because this this graph, I'm sorry, because this graph k d plus 2 minus an edge is the rigid, that's a basic fact, and of course the closure itself, I'm sorry, the closure of the random graph contains the graph itself, and then we just have a probabilistic lemma which asserts that asymptotically almost surely over over G and M for this M, the only graph that can have these three properties is Kn, and the closure must be everything. Hence, the graph is rigid, and I just want to say that if I would omit this assumption, then I would have been very false, and to make it true, namely to say that these two properties imply that that the closure is Kn, requires a much denser GNP. This is known as the K d plus 2 bootstrap percolation problem. So these are the two main ingredients of the proof, and let me spend the minute I have and another one that I don't have on some open problems which I find very interesting. So we talked here about the our connectivity threshold. There's of course another super important threshold in GNP theory, which is the emergence of a giant component, and we still don't. We still don't know exactly what is the exact critical probability for the emergence of a giant rigid component, and we don't understand this interesting phase transition at all. Another question is to go up in the dimension. So here we talked only about a fixed D. I want to ask different question, which is, for instance, what is the our largest dimension in which a Gn have a uniform organograph is rigid, and we still don't know if this dimension is linear in n. And the third question that I propose is about the rigidity of random regular graph. So we understand it when this equal to 2, but for higher dimensions, it is completely open. Thank you very much.